go back. Anyway, as I said, I'm very pleased that you all are, engaged in or asking some questions, which is fantastic. So anyway, feel free to interrupt me anytime. Here too, we'll actually do a little bit of revision, okay, and then we will also do a few things. So the first thing again I will ask you is building on what Vaidhi talked to you about, physical processes responsible for emission to jet and what are the diagnostics, what we found out. And then we'll also look at the total energy carried by the jets, how do we estimate that, what are the effects of interaction of jets with the host galaxy in the environment, how fast the jets moving, and what are the observation consequences. So initially, we will do a little bit of revision, then we will try to ask new questions that we are posed to. Right? This is something which you already know. So that she asked the question on the opening angle. And so what is the emission process responsible for the emission jets? Synchrotron emission. And synchrotron emission, is highly relativistic particles moving in a magnetic field, right? Relativistic particles. Now, what is the spectrum of the emission? It's sketchy, it doesn't matter. This, like this. Okay. Actually, this is apparently too small, right? I mean, you give visibility to the board which is visible. But could you all read this or no?
Yes.
You could read it. Over there? You could or could not? Could. Anyway, I'm trying to write a bit. So I can rub this out?
Yes.
Yeah. So we'll quickly revise what you already know. I will go rapidly, but at least the spectra, I will try to explain it. Okay. Things where I think you already start. I will try to explain it. So this is something which you already know, that it is a relativistic electron moving in a magnetic field. So depending upon the energy of the electron and the energy and the strength of the magnetic field, relativistic electrons can give rise to synchrotron emission right from radio frequencies at the low end to X-rays and gamma rays at the high. Okay, and as she pointed out, that the opening angle is 1 gamma, but we sort of discussed that is no issue in terms of predicting the jet because you have a whole range of energies, you have a whole range of pitch angles between the field and the source, and also the field is random, so emission will come out in different directions. But when the whole jet is moving towards you, then you find that the emission is sort of, you have to apply the special relativity transformations to solid angle to get the observed flux versus the flux. So the Lorentz factor of the bulk motion of the plasma is different from the motion of the electrons. So we'll try to distinguish that whenever it's necessary. Right? Now, okay. So this anyway, people know, but so just to keep a ballpark number in mind, that if you have an individual electron with a Lorentz factor of 10 to the power of 4, which is 10,000. Right? 10,000 is, I think that must sound all right. It's about 9999 of 10 c. So you can see it's almost the velocity of light. And this in a magnetic field of 10 microgauss, which is a typical magnetic field in the dome of a radio galaxy. Okay. You get emission at 1 gigahertz. 1 gigahertz is slightly more than 20 centimeters. Right? So you can see that even when you have 10 to the power of 4, you have energies which are, nearly the velocity of light, which you only get at 1 gigahertz. If you want to 1 gigahertz is 10 to the power of 9 hertz. But if you want to go to the X-ray region of the spectrum or gamma ray, you need 10 to the power of 17 18. So you can see how really going to accelerate these electrons. to very high Lorentz factors to be able to get synchrotron emission at X-rays and gamma frequencies. And we saw a picture of the X-ray jet of 3, but there are a lot of jets and quasars which have been mapped or imaged with the Chandra telescope at X-ray wavelengths. Now, if you had a single electron, what happens is that this is what she was asking: a single electron, let's take an idealized condition, radiating in a aligned magnetic field. Then a single electron will emit most of its energy at a particular frequency. There would be a certain range, and that is probably what she was talking about when trying to draw this. that you would find that the energy, where most of the energy is emitted, is about roughly 4.2 gamma squared p perpendicular. These are in CGS units. So what happens is that if you were to plot some function of u upon c, okay, say flux, and u upon some particular frequency, to go like this with bulk of the energy at a particular frequency, at a particular energy, and the strength of the magnetic field is emitted, is given by this. So we increase gamma, then this peak is going to shift to high frequencies. If you increase p perpendicular, it's also going to shift, but not as much because there is a square dependence over here. So when you're talking about X-ray wavelengths or gamma ray, jets and X-rays or gamma rays, you need much higher values of gamma ray. Magnetic field, as I said, also plays a role, but less so. Now we try to understand what is how do we get the kind of spectrum which we see at now we saw that suppose I want to draw, you can see this is the nucleus jet over here, and say this is the node. Okay, and this is the core associated with the galaxy, and this is what I call the node, and this is the jet, and this is the then what I have is, if I plot the flux density over here as mu versus mu on a log scale, this is log of this mu over log mu, then I will get a spectrum which is sort of schematically like this. In the core, I will get a spectrum which is more complex. In fact, jet, I will get a spectrum which is not as steep, usually a bit flatter, and low is a steep spectrum. Now, why do we get this shape? The reason is that it goes back to the earlier statement we made that when you look at the particular electron of energy, then the flux or whatever this energy, whatever you call it, u upon u c, that higher energy electron would emit more energy at a higher frequency compared to one at low frequencies. So, for example, if I had, what this shows is that if I had electrons of a lower energy, that would emit at a lower frequency. If I had electrons at a higher energy, then I would have electrons emitting at a higher frequency. Now, to get a power law slope, okay, this is what it looks like for the power law, and one can write it as S mu is proportional to the power minus alpha, where alpha is the spectral index. And this is, just some typical values, 0.8 to 1 or so. This is about 0.5. And this is more complex. So that how do we get this? Get a spectral index of either 0.5 or 0 or 1 or complex. So what happens is that if I had a processes by which I have more electrons at a lower energy. So here I've plotted the flux density versus frequency. Here I'm actually writing down the energy of the electrons and how they are distributed. I have many more electrons at a lower energy compared to electrons at a higher energy. I can express this as NEBE is proportional to the power of minus P, say. What it tells me is that the energy distribution of the electrons which are radiating or giving rise to the synchrotron emission from the lobes is also a power law, right? If I start off with a power law distribution, okay, of the radiating electrons, then what I will get is a power law in terms of the flux density of the emission which I see on the source of emission, provided it is optically thin. What does optically thin means? That none of the radiation is getting absorbed within the source or in its vicinity, right? And I can actually relate these two. This is shown over here, that this load is related to this load, right? This is equal to alpha, right? And detailed theory one can work it out, but just to give you an idea that lower energy electrons over here, they are so all these lower energy electrons, although they are emitting less power, they will add it up, give you more flux. There are fewer electrons over here, and accordingly you will get less emission, although because of the higher frequency or higher energy, we are radiating more energy. Because of the lower number, we get this smaller currents. So, if you look at the spectrum of the lobes of radio sources, they are very tenuous. Source is not getting absorbed. Emission is not getting absorbed within the lobe. So, a parallel distribution of the relativistic electrons, which are giving rise to synchrotron emission. Okay, the electrons have a power energy distribution giving rise to a spectrum which is a power, which is stable. Right? Now, in the nucleus, what is happening is, without getting into details of the absorption processes, the emission is getting absorbed. Because something is very compact, there's a lot of gas and dust in the nuclear region. So the nucleus often has a complex spectrum. The jet, what is happening is that it is optically thin, still has a power, is slightly flat. And that is believed to be because of various reacceleration processes which are taking place quite intensively as the jet is going out. You see that when you actually see a picture of a jet, you see various knocks. There could be shocks in the flow of the jet. And that is how the spectrum turns out to be a bit flat. Now, you can ask yourself, why is the energy electron a power? Right? That is another question one can ask oneself. So, the people have worked out various shock acceleration processes which may be going on within the lobes, which gives rise to this power law. But we will not sort of get into that. Some of these processes were actually worked out by Fermi long time ago, where electrons bounce out magnetic irregularities, and these are called Fermi acceleration processes, first order, second order, etc. But we'll not get into detail, but just know that a power distribution of the electron energies due to acceleration processes going into lobes gives rise to a power law observed spectrum when the source is optically thin. This is true of all sources which are optically thin and emitting synchrotron radiation. So this has become one of the diagnostics also of trying to see if the emission is thermal or not. Is it synchrotron? If it has a power law distribution, then it is very likely to be synchrotron emission, at least at the frequency that we're talking about. Okay. The other signature of synchrotron emission is that it is polarized. And the magnetic field is very uniform, you can get very high degrees of polarization, 70-80% or so. And you often see that kind of degree of polarization in these lobes of large radio sources. So polarization and long-term spectrum becomes a diagnostic of trying to identify lobes or jets of synchrotron emission. Core spectrum is usually more complex because of the absorption of the emission at different frequencies by processes which we will not delve into detail, but thermal absorption by the dense gas in the central region, as well as the synchrotron emission itself getting absorbed in compact knots of emission in the jets. Okay, so that is synchrotron emission. You've also heard about when Vaidhi talked to you about high frequency emission. He talked about an inverse Compton process, right? So inverse Compton, you may have studied a little bit about the Compton process in your undergraduate classes. So Compton process, when you look at a stationary electron, your photons coming in, photons go out, transferring momentum, and the electron and the photon loses energy, right, giving it to the electron. But here we're talking of a situation where there are highly relativistic electrons and there are photons. So, on a certain condition, the photons actually can gain energy at the expense of electrons. So you have a photon-electron interaction, but the photons are actually gaining energy at the expense of the electrons. So the photons can get pumped up into higher energies by taking the energy away from the electrons. And so that is a process by which a photon is new, and as we just saw, this just can go up by gamma squared. For example, what we talked about 1 gigahertz photon, which is 10 to the power of 9 hertz, and if it has a relativistic electron of gamma of 4, that if conditions are right, a lot of these interactions which can take place, then you'll find that gamma squared is 10 to the power of 4, that's 10 to the power of 9. So the inverse complex scattering photon would be about 10 to the power of 17 hertz, which is in the extreme spectrum. So, for example, when we talk about the spectral energy distributions at high energies for some of these objects. So, if you had a part or distribution of say radio photons at and then some of it gets upscattered to the X-ray region, you get a similar kind of spectrum in the X-ray region of the spectrum. You'll get a non-thermal spectrum with somewhat similar slope and a similar slope, but at the high energies. So, this is an important process in understanding the emission processes at high energies, particularly at X-rays and gamma rays. Okay? Because sometimes you might find that the synchrotron energy distribution goes on to, extends to high frequencies, but it doesn't always happen, as we shall see in a short while. Okay? Now, this is spectral radiation. Now, when does this become important? For example, it depends on the photon energy density in the magnetic field, whether the inverse complex process dominates or the synchrotron process. So the photon energy density is large compared to the magnetic energy density, because the magnetic field is what plays a role in synchrotron radiation, right? The synchrotron radiation is gyrating in the magnetic field. Inverse complex is where the photons are taking energy off it. So the photon energy density is larger in the magnetic energy density, then the inverse complementation comes into play. But on the other hand, if the magnetic energy density is much larger, then the synchrotron radiation dominates over inverse complex processes. So in practice, both these processes can keep occurring simultaneously, but which dominates depends upon the ratio of the photon density towards the magnetic. So when the photon density is large, which means in compact sources, then inverse content can dominate over synchrotron sources. And also at high redshifts, for example. High redshifts, why? Because you heard about the cosmic microwave background radiation, right? And that radiation energy density keeps increasing with redshift, right? So because it increases with redshift, we have these lobes of emission where the magnetic field density is low. You might find that the inverse content radiation density is more than the magnetic density. The inverse content radiation can quench the source because it's taking away energy and putting it in the X-ray region spectrum. We see applications of this in real situations. Okay, but just remember now that both these processes can play a role, and depending upon the ratio of the photon energy density to magnetic energy density, inverse content or synchrotron will dominate. Right? Now, what happens in a real situation? For example, we talked about a hadron value class 1 sources, right? Which don't have hotspots, have diffuse plumes of emission. Now, if I want to see what dominates, is it the synchrotron process or is it the inverse content process? One thing is to first look at the spectrum of the object. And see if the same electron energy spectrum extends to the highest energies of the object. For example, if the X-ray emission is much lower or much higher, then what I get by extrapolation of this, and some amount I can take care of by the process, then I have to invoke something else. But if it is a continuation of the same spectrum, then you can hold your heart in your hands and say it's likely to be the same emission process, the same electron distribution. So when I look at that, when I look at the hadron Friday class 1 sources, right from radio to the X-rays, it seems to be reasonably well fitted in most cases with a single spectrum. Because the jets and its loads are fit by a single spectrum, they are likely to be synchrotron emission right across the energy range from radio to the X-rays. Okay. But when it comes to the phanerophile class 2 sources, okay, this is just showing you an image of it. Okay. This is a Taurus A image jet where the contours are written, the X-rays are bronze color. You can see the close correspondence between and X-ray emission. But if I look at the phanerophile class 2 sources, which are very asymmetric jets and prominent hotspots, that spectral range distribution cannot be extended to. So one has to invoke some other process like inverse conflict scattering, but one also finds that it doesn't provide a very satisfactory explanation. So one possibility which has been talked about is that in these jets, what you're seeing is not just the inverse conflict, just not the cosmic microwave background radiation. If you position yourself on the jet itself is moving at a high velocity. Because the jet is moving at a high velocity, you're seeing an enhanced intensity of the CMB radiation. So the Doppler effects begin to play a role because the jet itself is moving with a high Lorentz factor. So this is the bulk Lorentz factor of the jet, and it is not the Lorentz factor of the individual electron. Okay. So gammas over here can be about 5 or 10 or so, not of the order of thousands that we talk about for 10 to the power 4 or even much higher for the individual electrons. But even these jets which are moving out can have high Lorentz factors of a few, about 10, 20 is what we talk about. But because it is moving, look at the cosmic microwave background radiation from the reference frame of the jet, the apparent energy density is. So you can see that these processes are responsible, are responsible for the emission which we see at different frequencies, and one has to do detailed modeling to try and see what components are dominating in the different kinds of sources. And obviously one needs to make measurements not only at radio but across the electromagnetic spectrum. At gamma rays we don't have the resolution, but X-rays, the Chandra telescope has provided information on a lot of jets which they are imaged with about half an ounce resolution or so. Actually, really the highest resolution X-rays that we see. Here it's a very southern source with X-ray emission here and the corresponding radio emission here. It's also picked up a hotspot over here, and you can see that not very close corresponding, but there is a lot corresponding between knots of emission, which may be due to shocks in the flow of the jet, or it could be due to individual plasmons which are being shot out from the black hole with disk at successively different points of time. But these knots are very common in the jets, in these jets, class 2 sources. Any questions on that? Feel free to interrupt me. Now the next question we'll ask ourselves is, we saw these loads of radiation, and we want to know what is the total energy. Well, ultimately that energy has to be carried out from the nucleus to these loads. And we'll see how these jets carry energy. But first we'll try to estimate what is the total energy in these loads. Now, what does the total energy consist of? It will consist of the energy of the particles, right? And the energy of the material. What we observe? We observe the emission from. Say we observe the radio emission from, and we want to see that in this radio lobe, what is the total energy? What can we measure? We can measure the flux density, right? Flux density, the units are watts per hertz per meter square. You get the luminosity, I have to multiply by distance squared. So the luminosity will be watts per hertz, right? So I can calculate the total luminosity of the object because I can make measurements across the radio spectrum. I know the spectral index. I can integrate over it from the entire radio window, maybe 10 megahertz to about 100 gigahertz, and I can calculate the radio frequency. That to me is an observed quantity, right? Now, to calculate the energy in the particles and the magnetic field, I have to get back to synchrotron chain. Okay? So, without getting into too much of detail, what I will just illustrate to you is by the expressions that we get that if I look at the total energy in particles, for a given luminosity, we know that the energy will be more energy will be emitted, magnetic field is larger. Uh, so for a given luminosity, it varies as total energy in electrons, luminosity multiplied by 3 to the power minus 3. So what this graph is showing you is the total energy as a function of total energy values. Things that what we measure is the flux density at radio frequency. Flux density is due to synchrotron emission. Synchrotron emission is due to the relativistic electrons. But overall, it has to be charge neutrality as well. You can't have charge separation systems. So the thing is that protons or heavier particles are present, but it's very difficult to accelerate them to the kind of electrons, the kind of energies that we can accelerate electrons. But when we want to calculate the total energy, we have to factor in the fact that there are also heavier particles, protons and some heavier particles. But we often don't know it down. And that is why we use this number, use this fudge factor K. From galactic cosmic rays, we could put a factor of 50 or 100, but we don't actually do it. So usually people tell you what number they use so that you can explain the number. So you find that the total energy in electrons is square. You know the magnetic energy density is given by V squared upon E5, and total energy in particles in magnetic field is multiplied by the volume. Get it into V squared. So that is what we have as the total energy content. What you see over here is that in the particles it varies as V to the power minus 3, magnetic field varies as V squared, and there is a minimum. If you differentiate this equation and get it, then you can calculate what is the total minimum for it. And the total minimum occurs when there is rough equipartition between the energy in the particles and energy in the material. So by solving this equation and knowing the luminosity of the source and the speckle index which you use to calculate the total luminosity, then you can calculate what is the total energy content of the source. Okay. Right now, without actually delving detail in secret theory, you have to take my word for it. But various sort of tests have been done, and although there may be some departures from this, but it is not very large. So this gives you a reasonable idea of what the total energy of the particle is. And when you do the sum, the kind of numbers that you get are about 10 to the power 60 to 61. So this famous source that we say, which we saw earlier, if I integrate from 10 to the power 7 to 10 to the power 11 first, this is the ballpark number of GT. It's about 10 to the power 45 ergs per second. So you remember one of you mentioned about 10 to the power 33 ergs per second for the sun. This is about 12 orders of magnitude larger than the sun, solar luminosity. And this luminosity, which is see the luminosity of the galaxy, and the energy, all this energy originates in the nucleus and is carried by jets to on the outer layers. Now we have to find what is the best way of generating this about 60 ergs of energy, which the jets are going to carry. What is the most efficient way that we can do that? Now, as I mentioned in the last class, actually I'll share these slides with you. So if you feel better concentrating on the slides and just thinking about it, you're free to do that. If it helps you to write something, feel free to write. Whatever you're comfortable with. But I'm quite happy to share these slides with you so that you don't have to write it. If you need the slides and give me the reference also to go back and look at the okay. Now what you can do is you can think of a proton of mass n falling from infinity, and just by conservation of energy, what you get is the kinetic energy is equal to G F n. So as the potential energy becomes more and more negative, as it gets closer and closer, it's bound up, kinetic energy is going to keep building up. And ultimately it's going to stop. It's a hard surface. Right? So what happens to it when it hits a hard surface? Some of it may go to internal energy, but most of it is related to gas heat, which actually is responsible for the X-ray binaries that we talked about. Earlier today we talked about X-ray binaries. So X-ray, why is it visible in X-rays? Because it gets heated up to a very high temperature. The accretion disk gets heated up to a very high temperature because the accreting material deposits its energy as its velocity increases, approaching the compact object, and heats up the material in the accretion disk to millions of degrees Kelvin, and it radiates the X-ray material spectrum. Okay. Now, I've written down the luminosity, specific luminosity of this object. It's the rate at which mass falls into half VPM squared, and you can use this expression to this expression over here. If free fall squared is 2g over r, and I can express the luminosity in terms of what is the Schwarzschild radius of the object. I don't know if you have done the Schwarzschild radius, but it is a solution for a stationary black hole, and within the Schwarzschild radius, light is not going to right? All the information is lost within the Schwarzschild radius. It is from outside only, but light can actually travel out. The last stable orbit is about 3 times the Schwarzschild radius. Okay. But this is for a stationary black hole. This is often used as a measure to find out how far away you're from the black hole. Right? So if I express this in terms of a Schwarzschild black hole, Schwarzschild radius. Any object can have a Schwarzschild radius. I mean, you can have a Schwarzschild radius, the sun has a Schwarzschild radius, the moon has a Schwarzschild radius. But usually for all massive objects, Schwarzschild radius is minuscule. I think for the sun, it's a couple of kilometers or 3 kilometers, the moon is a few millimeters. So the physical size of the object is much greater than the Schwarzschild radius. But in a black hole, the Schwarzschild radius is larger than the size of the object. So it becomes a relative quantity. Otherwise, the Schwarzschild radius is right very within the physical object that is talking about, and it's not relevant. Then I can express the luminosity in terms of real c squared RG upon R with RG. Now I can use this half RG upon R c squared, half RG upon R as a kind of efficiency of conversion of mass that is being accreted into luminosity. Right? And if I look at these values, I've talked about, put over here numbers for 2 condensed objects. One is a white dwarf. A white dwarf is a remnant, a stellar remnant of a low mass star like our sun. That was a white dwarf. And our sun will end up as white. Right? Whereas massive stars, greater than about 8 times the mass of the sun, will end up as a neutron star. Right? Now, white dwarf is larger in size. It's so 1,000 kilometers. This is about 50 to 10 to 20 kilometers in size. Now, if you look at this, so if you look at the efficiency, this is about 3 to 10 to the power minus 4. Neutron star with the more compact object, masses are similar, that you have an efficiency of about. So you can see that if I compare that with nuclear fusion, if I have a compact object like a neutron star, which is about mass of the sun, which is about 3 times 10 to the power 20 grads, I squeeze it to a radius of about 10 kilometers, even smaller than the size of Pune. Then I have an object whose gravity is very large, and the efficiency, because of that, is much more efficient than the nuclear reactions than you get from nuclear reactions. So you can tell yourself that if I had an even more compact object like a black hole, I should be able to do with that, isn't it? But black hole, if you just drop it straight away, it will go through the event horizon and go inside and be lost. But usually what happens is that matter which is accreting has a certain angular momentum. And because of that angular momentum, it will spin more and more rapidly as it gets closer and closer, and it will collapse along the axis of rotation because centrifugal forces will support it over there, and you'll get a disk. And the accreting material will actually deposit energy in the disk. And the closer you can get to the last stable orbit, the more energy you'll be able to extract out from the accreting material. Okay. Now, that's what basically they say. In practice, the body matter is angular momentum. Matter can fall onto the black hole, it loses angular momentum. That is achieved by viscous forces, which act in the disk. And some of the angular momentum actually, with these calculations, get carried away by outward expansion. Some of it carried by the jet. And viscosity acts as a frictional force, resulting in the displacement. So, more detailed calculations using general relativity for a Schwarzschild black hole gives it about 0.06, whereas a Kerr black hole has about 42%. A Kerr black hole is a rotating black hole. Solutions which were worked out by Frank Kerr, and that is really because in a rotating black hole you could get the last stable orbit to get much closer to the black hole than you could get with a Schwarzschild radius. Now, one asked oneself that if I put N equal to psi Tm c squared, if I keep increasing dm dt, if I create more and more matter, suppose there is a galaxy-galaxy collisions and there's a lot of matter which is coming into the black hole, can I get larger and larger amounts of energy if I keep increasing dm dt? I don't know if this has been discussed earlier, but can we or can we?
We can up to certain limit. So we can up to certain limit.
Up to certain limit. Up to certain limit, very good. Excellent. Up to certain limit, does anybody want to add or you want to add to whatever you have said? Up to a certain limit is good.
Pauli.
Sorry?
Pauli exclusion.
Not Pauli exclusion. Not Pauli exclusion. Pauli exclusion will come into play when you're doing matter where all the sort of levels are filled up. This is where you're just accreting matter onto a compact object. What you're saying is there's a limit is absolutely correct. When I give you the answer, you'll say, oh, I should have so think about it for half a second, half a minute. Or there is a limit, as she has correctly pointed out. But what could be the reason? She's just got the right name now. I think just okay. So there's a limit. She qualifies as I say it's a predicted limit. Sorry. Sorry. So what she's saying is that radiation pressure may be playing a role. Okay. So all three of you put together get the correct answer. Now, okay. So what happens is that if you're accreting matter and matter is losing heat, so obviously there is radiation coming out, right? As we saw in the instruments. So the question is whether radiation pressure can counteract the effect of gravity. So ultimately, the radiation pressure, if radiation gets larger, the effect of gravity, then it's going to halt the accretion process. So that is what Arthur Eddington pointed out long time ago. Although the calculations are more simplistically done for spherical accretion, but it is something which seems to hold even for when you have an accretion disk. We rarely exceed the velocities which exceed the Eddington limit. Of course, this excludes violent phenomena like supernovae or gamma reverse. Still, the accretion here. So, what time are we supposed to finish? 5:15, is it?
Yes. 5:15.
5:15. 5, is it? 5 or 5:15? 5. 5. Oh, you will finish it.
5:15.
All right. Okay. So that is. So I will not. I'll send you the steps because I can share the slides with you. So I'll not get into detail, but I'll just explain the physical aspects. Now, as we have already pulled together your resources and gave the right answer, that radiation pressure and gravity are so high, interact with each other. There's a very nice derivation of this. This is a more detailed book on accretion power of astrophysics. For some of you who want to really study it in depth. But there's a very nice sort of short description in Longay's book. Malcolm Longay's books, if you study astrophysics, They're very good actually. They give you a nice physical insight and simple derivation. Sometimes you put more complicated derivations for the more advanced treatment, but basically what you have to do is you have to calculate the pressure due to radiation. And how does the radiation pressure exert itself? It is due to Thomson scattering, because electrons and photons interact with electrons, all right? And but you can't really have large separations. Electrons and protons are combined together to get this overall neutrality. So you need to balance the effect of gravity due to radiation. So I will just briefly mention about this. Gravity is gm upon r squared. As you know, it can include a mass of the electron compared to the proton. So gravity acts on the proton, but photons act on the electron, and you can calculate the amount of momentum which is given by the proton. Proton will collision with the electron, but the total effect of it, the total force, will depend on the flux of incident photons and photon. And n photon will depend on the total luminosity of the object. Right? So you can calculate the luminosity of the object, then 4 pi r squared is the dilation due to distance, and divided by the energy of the photon, number of photons, okay, flux density is by, the force due to the photons is sigma t, number of photons and the momentum it gives us, and then you can calculate force due to the photons, scattering of electrons, equate to 2, and then you can get an expression for the maximum luminosity that you can get. This is what is called the Eddington luminosity, right? Okay. You get in longest book, there's slightly more detailed derivation than what I've done over here, but you can look at it more carefully when I share this. Okay. Now, the beauty of this is that if you look at it, then the only parameter depends on everything else cancels out. It's a mass of the object. Mass of the object, right? Now, if you actually put in all the fundamental constants over there, G, mass of the proton, C, and the Thomson scattering cross section, get an expression 1.3 to the power of 31 m upon n sun watts. Or if you want to put it in CGS units, if you're comfortable with that, 10 to the power of 28 volts per second. So if you look at the luminosities of X-ray binaries, which you looked at earlier and I skipped a slide, you will find that they're generally within about 10 to the power of 30 volts per second. That is because you're dealing with usually about a solar mass kind of object. Like a neutron star, black holes could be more, but it's in an order of magnitude. But when I talk about active galactic nuclei, what is the kind of black hole mass I'm talking about? What is the mass of the black hole in the center of our galaxy? There's a few billion solar masses. But if I'm talking of active galactic nuclei, what is the mass that I'm talking about? Sorry? It can be up to a billion or so, yeah? So let me take as 10 to the power of 8. So if I put in 10 to the power of 8, the maximum luminosity I get is about 10 to the power of 46 volts per second. Okay. And when we look at actual measurements of masses of black holes, which very sort of touched upon, but I don't think we'll have time to get into different methods of. If you have questions, we can take that question time. That for AGN, you will require much higher mass function. So if you need to be able to generate the kind of luminosities of active galactic nuclei of 10 to the power 46 Earth per second, you need 100 million solar masses. That will be the maximum luminosity that you can get. And the observations are broadly consistent. Okay, I have what put this away now. So luminosity you can see for extreme binaries, it's of the order of 10 to the power 58, whatever low mass binaries. Low mass and high mass are defined by the mass of the galaxy. Okay. Whereas when we talk about AGN, it's of the order of 10 to the power 8 solar mass. Now, you can also find out at what temperature the black hole would be emitting. Because what is happening over here is that it is a thermal process, right? Matter is getting accreted, the heating of the accreting material, and the accreting material is radiating like a black body. But it does the spectrum, if you look at it, doesn't exactly look like a black body because each part of the disk is radiating at a different temperature. just like the sun is much hotter at the center than it is so similarly with equation disk. If you look at the effect of gravity and how the matter is behaving, you find a much higher temperature closer to the black hole than outside. If you look at the spectrum, it's not going to be a Planckian curve, but it will be the sum of many factors, right? So if I were to just for argument's sake put the luminosity, okay, I use the Stefan Boltzmann law, L is equal to 4 pi r squared sigma t to the power 4 for a black body, and I equate that with the velocity, I can get an estimate of the temperature. So I can calculate what that would be for a solar mass black hole, I can calculate for white dwarf, I can calculate for supermassive black holes. And then you will find that the temperatures you get are roughly consistent with what you actually measure. Neutron stars, if you can detect them, you'll see them as extremely hot, extreme power. So at least the first approximation from just very simplistic arguments without doing very detailed modeling, you can get at least an intuitive picture of what is happening consistent with the observations. Okay. Now, for supermassive black holes, what happens is that there is no radius over there, right? There is no radius over there, but what is the radius is the, say, the last stable orbit kind, and that is 3 times the Schwarzschild. So what happens is that the more massive the object is, the Schwarzschild radius also gets much larger. So if you look at quasars, for example, you'll also get temperatures which are in the ballpark of about 2 to 10 to the power of 5 Kelvin, which will give you a peak in the ultraviolet optical region of the electromagnetic spectrum. Similarly, for white dwarfs, you get a peak. Sorry, go ahead. I think even if it has a spin, what is going to happen is that you still have an accretion disk. It's a question of how close you get to the black hole. Okay, so if it gets closer, you'll get a hotter spectrum. But independent of that, you get slightly closer, that's true. But on the other hand, it's not going to shift a lot. So you get still a bump in the ultraviolet region of it. Right? And if you look at the actual spectrum of an object, this just says the same thing. I just written out the Schwarzschild radius of different objects over there. You can look at it. So this is a spectrum. A similar spectrum was also shown by Wendy, that this is the ultraviolet blue bump, and this is the one which is this is often referred to as the big blue bump. So these are sort of indications that our broad picture of energy being due to accretion is a reasonable sort of scenario with which to work on. Accretion of material of the supermassive black hole and extraction of energy from this black hole by this accretion disk is what is generating the jets which power these extended lobes of radiation emission with a total energy content close to about 10 to the power of 60 Earths or so. So as long as you remember that accretion is a process which can be highly efficient when accreting onto particularly a rotating current black hole, I think at this stage it would be adequate. You can sort of read up more as you progress learn into the Now, in 10 minutes, we will look at what are the possible effects of such jets. And today, I think we'll probably close at that. We have 10 minutes to go. Now, once you generate a jet, once you generate this jet, then as it traverses outwards, right, it's going to affect all the material around it. Right? Now, we have talked about, you learned about star formation, and you talked about gas which has to be dense and cold so that forces of gravity can be overcome to condense into a star-sized object. Now, in this scenario, beautiful scenario where molecular clouds are there, you shoot out this kind of jet. It's going to affect the galaxy, isn't it? And that is going to affect the whole history of the galaxy. These stars are going to form. Now, the interesting thing is that what do you think will happen? Do you think star formation will stop? Or do you think star formation will get enhanced? Or do you think there will be no significant? Sorry, will we enhance? Will we enhance? What do you think? It could be both. Okay, very good. There's one enhanced and one's both. So which side are you going to take now? What do you think? Could be both. So everybody agrees with them or disagrees with them. What do you think? You don't agree with it. No, okay. That's not an extreme view now. The other thoughts are what might happen. Actually, the answer both is correct. Okay. Now, for example, what happens in certain cases, it is seen that the jets can compress clouds. Ultimately, you need to compress the clouds to start formation. Right? So there are examples. I've just picked up one example. This is a famous object called Minkowski's object. And this is a relatively nearby object called HC 541, which is a regular galaxy. And you can see this jet is hitting this cloud of gas. And you can see the evidence of this star formation here. And if you look at this cold gas in both molecular hydrogen, molecular carbon monoxide, which is the purple color over here, and neutral atomic hydrogen. So neutral atomic hydrogen is it's also cold, but not as cold as condensed. And there's quite an interesting correspondence between the jet is hitting it and you see star formation. So jets, in a way, can compress clouds and trigger star formation. And there have been other pieces of evidence as well. For example, sometimes the central regions where it goes, you can see a slightly shape of the bulge over there, not bulge, where the jet may trigger star formation tries to association with the orientation of the jet. So that is a possibility. Okay. And this was actually suggested by Martin Rees, a very well-known astrophysicist from Cambridge, very close friend of IUCAA, where they must know it very well. But this is an example. But if you look at the other aspect, that if I, for example, let a jet go out, I'm also going to heat the gas, right? I'm going to deposit it. And that is particularly true of this Fedorov-Riley class 1 jets. Because it's not a very narrow thin jet which is going on, but it broadens up, it entrains material and forms these extended planes of emission. So Dipanjan, my colleague from here, I don't know if he gives some lectures, right? Dipanjan actually does a lot of interesting simulations on what happens when these low power jets enter a galaxy. And what that shows us is that these low power jets actually spend a lot of time in the galaxy because it's not a high energy bullet going through kind of thing, which is true with Fedorov-Riley class 1, class 2 jets. So because they're spending a lot of time, they're dissipating energy, they are heating up the interstellar medium. And once you heat up the interstellar medium, then you're going to get a star formation. So compressing a gas cloud can enhance star formation, but general heating up of the medium can also diminish star formation. The other thing is that jets can also train material and completely take it out. So if you take out a lot of molecular gas from the galaxy, then they're going to decrease star formation because it's these cold clouds which are playing a role. So the answer is that jets actually play a very important role in the evolution of galaxies by affecting star formation. And so the whole history of galaxy evolution is something where this is a process which has to be taken into account. And this broadly goes by the name of feedback, because the jet is feeding back into the properties of the galaxy. And the creating material, creating the jets, and then feeding it back. And these feedback processes are extremely important in trying to understand evolution of galaxies over cosmic time. A lot of properties of galaxies, which are not getting into detail over here, are much better understood with a good handle on the feedback processes that are taking place. Here I have actually just shown a schematic illustration of, this is based on observations which they have done with Kusuman et al. Report a couple of years back, where they have looked at the dynamics of molecular clouds as well, where the jet increases to some degree is expanding out, creating a cocoon of hot gas, which is actually heating and pushing molecular gas. And so you see evidences observationally of both the effects, where star formation is diminished as well as enhanced. So it's different set of physical conditions, but both effects are seen. So jets have a profound effect on the interstellar medium of the galaxy. The other aspect which I wanted to mention today about jets is that, you see, suppose, I mean, just like stars are not usually isolated, right? More than 50%, the majority of stars are actually in binary or multiple systems. So galaxies also are not isolated. They have their own social structures. They have their own clusters, groups, just like us. Okay. So in a cluster of galaxies, the galaxies are also moving about, and in the potential of the overall cluster. And in a cluster of galaxies, the total mass which is contributed by the visible galaxies which we see is maybe about 10% or so, even less than that. About 20-30% is actually the medium between the galaxies called the intercluster medium, and about 80% is actually dark matter, which you don't know anything about, but exerts a gravitational influence. But these galaxies are not isolated. They're not isolated, they're in groups, and because of the gravitational influence, they're moving about with high velocities, which is very rich clusters can be thousands of kilometers per second. So what happens to the jets when they come? Just like when you run, you feel the ramp pressure, which is proportional to density and the velocity at which you're moving. You run against the wind or run against the wind will achieve. It's a similar pressure. It can bend the jets in all kinds of directions. So the ramp pressure also affects the interstellar medium of the galaxy. I've just shown you the radio contours over here. Ramp pressure affects the neutral hydrogen medium, the interstellar medium of the galaxy, but the radio jets as well. So you can look for clusters of galaxies by trying to identify such structures as I mentioned. That is also being detected. And these are 4 examples of this. This is an example where a particular galaxy has 2 nuclei. Probably one is being swallowed up by the other, they disappears, but both of them seem to be active. So you can see all kinds of interesting structures. Now, in a cluster of galaxies, which I just mentioned, that there is much more matter in the medium between the galaxies than in the actual galaxies. Because of, again, residing in a potential where, due to the effect of just balancing gravity plus the random motion, this gas gets heated up to millions of Kelvin. So the intercluster medium is something which you can probe at extreme mediums. Because the temperature is very high, temperature is in the ballpark of millions of degrees Kelvin, so it is emitting the extreme region of the spectrum. Higher the energy, higher the frequency energies. Okay, higher the temperature. So these jets of plasma which are coming out from the galaxy affects this medium as well, and that affects the evolution of the cluster itself. And what you can see over here is a particular source called PCA4, where these are the contours under radiation, and you can see the blue over here. The color is the X-ray emission. You can see these cavities over here. These cavities are the ones where the radioplasma is actually pushed out the X-ray emission and not let it collapse. And so you can see the jets coming out from active galaxies also affect the clusters of galaxies. So jets actually have a galaxies. This is an example of a jet which is processing. Sometimes you see combinations of that. We'll stop here today. It's 5 o'clock. And tomorrow we will look at speeds and we'll go back to the unification scheme and we'll tie it together and we'll do a bit of disk jet connections and do a little bit of recurrent activity. So today we can take some questions. If you're, yeah, please.
So for you said that the star formation rates are affected because of the jets, right? So you have a fairly linear galaxy, like spiral galaxy, and the jets are sort of perpendicular to the galaxy. It's usually affected because they don't really interact much with the galaxy.
Very good question actually. And here, what happens is that what you're saying is true. That if you look at the spiral galaxy, one thing is that the jet direction has very little to do with the overall orientation of the galaxy. The jet could also be coming out along the plane. Okay, but most of these very luminous jets are actually associated with elliptical galaxies. They are not radio loud objects. But these low power jets in, for example, the spiral galaxies, super galaxies, they can also affect the dynamics of the gas visibility. You can see effect of it in the, for example, the width of the spectrum lines or the shape of the spectrum lines. You can also see neutral atomic hydrogen properties affected by the jet, which is coming out. But these are relatively low power jets, and how much effect it has with the orientation. What seems to be true is that the orientation of the jet is very closely related to the orientation of the ionization cone. But that orientation has very little to do with the overall orientation of the galaxy. So the fact that the ionization cone and jet are oriented also lends support to this whole torus and the jet orientation scenario. But they will have probably less of an effect because of the very low luminosity compared to in the elliptical galaxies where the jet power is much larger. But they do have it. Yeah. Okay. The last picture I showed was the precession of the jet. For example, if you had a jet axis which was steady, and there are many sources where the jet axis is very steady over, maybe 100 billion years. And how do I know it is steady for 100 billion years? Because if I look at some of the largest radio galaxies, how large is the largest radio galaxy? It's about 5 megaparsecs of the entire ballpark, right? That means 5 megaparsecs, 500 million parsecs. You multiply with 3 to get into the data. So it's huge, right? And if you put in, reasonable velocities of a fraction of the velocity of light, for the house force you're moving out, you can estimate time scales of 100 million years ago. And here we see that the jets are roughly pointing in one direction. The structure has not changed. So we know that in many cases, the jets can be steady to that time scale. But we also see cases, as in this particular example, where the radio structure reflects the jet. Now, if it is precessing, what is it that will precess your answer? The thing is that clearly there is a stable direction at which is emitting. Now, suppose I disturb that. I could disturb that by collision with the galaxy. If it is a binary black hole, that could also be the case. A dwarf galaxy may fall into a galaxy. So it is these interactions and companions which can disturb the axis of the black hole. Where in the binary system there could be effects of, and if you disturb it from the regular axis, you try to come back to its stable axis, process will come back. So basically, a steady direction disturbed can try to come back to its original. But this happens over such large time scales that you see the effect of the individual structures. Not a huge number, but a reasonably large, significant fraction where you see effects in precession. And the kind of radio structures you can predict because of precession. Because look at it. I mean, I have a precession jet. Now, what the structure will appear will depend upon how large the cone angle is, what it is inclined towards you. Suppose I have a jet pointing directly at you and it's precessing. The whole structure will look a bit circular compared to if it is over here and it is precessing. So you can reproduce a whole lot of geometries depending upon the parameters the way you play around with. But it is basically disturbing the ejection axis like some process.
Also, in these precessing tests, are they
Actually, most of these radio galaxies, when you see these very prominent jets, are associated with galaxies. There are very few luminous radio jets of the kind of jets we just associated with this galaxies. Just about half a dozen about them. And we still don't completely understand why this dichotomy exists. Because there are various suggestions, there is time to want to touch upon it, but we don't have it.
So next slide, why don't most of the electrical galaxies that are used, why don't they show a precession?
Why don't they show precession? Why don't all of them show precession? So clearly, the kind of interactions which are required to disturb the axis of the black hole are not in place. That is sort of an obvious straightforward answer. But to go a bit deeper, one would have to look at the environments and the properties of galaxies which possess and which don't, and see if you see a marked difference between the two. And which anybody has actually looked into that of the actual profiles of possessing versus not possessing objects, and see if there is a very clear difference. I can't remember offhand somebody doing it, but I'll check it out. Okay. The other question.
How do we know that we are observing a precise jet in different geometries?
How do we show? How do we know? Sure. I mean, this one, if you take a garden hose pipe with, this one is quite obvious, right?
Yeah.
It looks like an SGM structure. If it is more complex, it's not. I mean, people who push precision models will swear by it. People who don't will say, so you can't be honest. It is. I mean, you can. I mean, if you look at these models and what you get, you really get a very wide range. And it's your personal preference. Some are very obvious, but if it's not obvious, it's your choice whether you how seriously. Any questions from this side? No? We'll stop today? Yes? So is there anything you haven't understood? You understood everything. Anyway, my job is to just introduce you to it, because to understand everything properly, one has to read more and reflect more and all that. So this is more of an exposure and trying to give you some basic ideas. But I'm happy the way you all are interacting. Ask the question. To the website. Okay. So we'll meet tomorrow at 2:15, right? Yeah. So tomorrow we'll stop.